All right, good morning. Wow, 5 people. This would be a great time to give the answers to the final exam. All right, how is everyone today? Well, any questions? Otherwise, we're just going to jump back into hashes.
Good morning.
Good morning. All right, well, back onto hashes then. So, remember the basic idea of an associative array is that we have some sort of key. In our example, we're using license plates, and we have some kind of data. In our example, a person's name, and we're associating the data with the key. And so a hash is basically something that will take a key and use that to either store data or search for data or retrieve data from some sort of storage location. And so let's talk about what this looks like as an abstract data type, because every time we do a new data structure in this course, we want to think about it as an ADT, right? So what does it mean to interact with a hash? So what kinds of things would we potentially like to do with a hash? What sorts of functions?
I guess I don't know, searching.
Yeah, searching. What else?
Deleting.
Deleting.
I don't really think add would be very relevant. I mean, yeah, okay, well, you'd have to...
Some sort of way to get stuff into the hash. It might happen only once, or it might happen continually. Anything else?
Just to know you're not screen sharing or anything. I don't know if that's on purpose or...
Oh no, that's not on purpose. I'm just writing down what people are saying, but...
Oh, I see.
There we go. Alright, yeah, so what else? Add, search, delete. You got a database with theoretical order 1 access.
Well, you don't need to sort often because it's in a hash.
Probably don't need a sort. I mean, you might if you wanted your data in sorted order, but you would probably pull it out and then sort it. But how do we pull data out of a hash? Do you remember what we did with associative arrays?
Well, you can loop through associative arrays, right, in some way.
Yeah, remember it was kind of a weird thing to have to do. It had all this weird syntax associated with it.
Does C have a for in loop? I don't.
It does not. But we need something like that. So I'm going to use the word traverse. And this is a word that we're going to encounter a lot. Traversing a data structure. And traversing for us basically means going through it, sort of one element at a time. And figuring out what's in there. And for a linked list, traversing the list was easy. We just started at the sentinel. We just moved from node to node and printed out each element. Or, searched it or something like that. For an array, we can just run a for loop where the index starts at 0, goes up to the highest index, and we can get through every element like that. But with an associative array, we can't do that. We need something like a for in. And so there's going to be some sort of traversal mechanism. And we may not always think about it, but we need some sort of initialization probably to say, hey, I want a hash, make me an empty hash. And so that's probably a minimum set of interface functions we would need to work with this data structure. And we could imagine other functions we might do. We might want something to reset it to clear out, all the information that's stored in there. Or we might want something that tells us how full is the hash. Well, let's think about this sort of basic set. So, from our main program, we might say something like, we might have a type def called hash, and we could say hash, plates equals init. And that might create an empty hash table that we can reference using this variable called plates, which is defined to be a type hash. Whatever hash is, this is something that, there's some type def set up in an include file maybe. But we call init to create an empty. And then we can do the following items. We could say search for plates, comma, key. And this could give us back the piece of data associated with that key, or maybe a flag if it's not found, right? Maybe it will return null if this key is not stored in the hash. So if you want to search for license plate ABC123, we could search plates, comma, quote, ABC123. And it'll give us back a name like Nick or Izad, or it'll give us null if that plate's not stored. And then if we want to delete an entry, we would probably just say delete, put in the name of the license of the hash table, and then the key that we want to delete. And maybe that'll return a success or failure flag. And if you want to add something, right, just add, and we put in the hash table, and then the key and the data that we want stored. And this will create an entry under that key, and the data stored next to that key would be whatever data is. And typically, if you try to store something associated with a key that's already in the hash table, it'll simply replace the data associated with it. So if I have ABC123 associated with Nick, and now I say add, hash table ABC123 Phil, right? Phil would replace Nick in that hash table entry. And so this is not only for adding new data, but updating data. And then traversal gets interesting. So there's a concept we'll use very precisely in CSE222, which is called an iterator. But we can talk about iterators in 222, and we'll actually code these ourselves. And it's something like a for in loop. So we want to say, for example, let's print all key data pairs. We want to just print out the contents of the hash, just standard out. So here's what we can do. We could say something like, start iterator. And start iterator might say, begin to retrieve keys one at a time. Alright, so we call this once. This starts the process of going through a for in loop. And now we would have another function like, next key. And we could say key equals next key plate. And what this does is get some new key from the hash. This just gives us a key. ABC123, EE567. Something. No particular order, no particular rhyme or reason why it gives us one key over another, but this will give us a key it has not given us before. And so now we could do something like, name equals search. And let me change search to get or fetch. Because the way we've done this not only tells us if the key is in the database, but it also gives us the data associated with it. And if it gives us back null or some magic data, we'll take that to mean the key is not stored in there. So now I could say, let's fetch from our hash the data associated with this key. And now I could print these. And then I can go back up here. And every time I call this iterator, this next key function, it will give me another key from my database. And it'll be a key I haven't seen yet. And then I can use that, I can retrieve the data associated with it, print it out, or, tally it or do whatever it is I want to be doing. And I would just need, a way to exit this loop. So something like if key is null, then, I'll return or exit or do something, but I'm done printing out key data pairs. And so this pair of functions, something to begin iterating and then something to get the next element, is something we'll encounter a lot. And anytime we have a data structure that's storing information and we want to retrieve all that information, we want to go through it one piece at a time in no particular order. If there's no sort of defined way to do that, like if there's no sort of first element, next element, last element that we can do, we can write a pair of functions to iterate through the elements. All right, so that's pretty cool. So government opened a site a few days ago, one day last week, to get COVID tests delivered to your home, and they just showed up.
That was Jason.
Yeah. Never mind. Nope, I was wrong. All right. So questions about what our interface is going to look like. Because I want to start defining how we make some of these functions. I want to do this in pseudocode, and then I want to use this to build up to collisions, but I want to make sure we're clear on what the goal is here. All right. So the implementation of the hash is going to be built around an array. And with n entries in it, so indices from 0 to n minus 1. We'll just call this hash. Still isn't clear, but I think it'll clear up. Okay. So the way this whole thing works, right? You have some kind of key, and you put it into this hash function, and it gives you an index, and that index tells you where in your hash table you're going to store the data associated with that key. So let's call this hash function h. And let's say you want to store, so I'm gonna and I use the word put for my add function. And these are pretty typical, and the hash package that's most available in C, DBM or GDBM, uses put and fetch for add and retrieve. So put will mean add something to your hash, fetch will mean get something from your hash. So let's say we want to put ABC123 and Nick. Alright, so we say something like, index equals hash ABC123, and then hash bracket index equals Nick. Right, that's the essence of it. When you want to store a key data pair, take your key, run it through your hash function, find an index, and then store your data at that index in the table. And then if we want to fetch a piece of data, right, let's say we want to fetch ABC123, effectively we take ABC123, we run it through our hash function, that gives us an index. We take the entry at that index in our hash table, that's what we return. If you don't start asking questions, we're going to finish all of 222 in like the next 2 hours. We're not going to have anything to do the rest of the year.
It's been a while since I've done hash functions for associative arrays since 224. And some, I guess one of the questions I have is, when you're doing associative arrays, I looked this up recently, it's mostly about the key, which could be like a string, and then some value you give to that string.
Mm-hmm.
So
Yep.
So they're kind of paired in some way. So
Exactly.
if there's a certain value, you refer to the key as holding the value.
Exactly. Yeah, you got it.
Okay, cool.
All right, so sample hash functions. So one that we talked about last week is, add ASCII value of each character. So I'm going to assume here that our key is a string. So, an all-terminated array of characters. But, your key could be binary, it could be a floating point number, whatever. But it's something that, we can manipulate in some way. So we'll just pretend it's a string. So one way to find a hash value is to add up the ASCII code for each character. And if we have, say, a hash table that holds 1,000 entries, well, if we have a long enough string and we add up the ASCII codes, we might get a number bigger than 1,000. So we'd like to take this sum of all the ASCII codes and change it to a number between 0 and 999. And any suggestions how we can do that so that we don't, go outside the bounds of our array?
Sorry, to do what exactly?
To add the ASCII value of each character, but make sure that the number we end up with is something between 0 and 999. So that when we index our array with it, we don't go out of bounds. This is a trick. It's a little 215-ish.
Ignore all that. Just use a library. No, I'm just kidding.
Okay, yeah, that would work.
I don't know. How do you?
So here's something you can always do if you're trying to, like, let's say you want a random number between 0 and 11, but your random number generator gives you numbers between 0 and 2 billion. How do you change it to give you something between 0 and 11? You can always use the modulo operator. Right? So if I were to take this sum and reduce it modulo 1000, I'm guaranteed to get a number between 0 and 999. And I can use that as an index. So it basically just rolls over. If the sum of my ASCII codes was 1001, I would treat that as if the sum had been 1. And I would store my data right here.
To be honest, I was expecting Fermat's little theorem over again.
Oh, yeah, yeah. We could do that.
Which theorem?
Fermat's little theorem.
What's that?
You in CSE222?
I am.
Yeah, we're starting that this week.
Oh.
So it relates to powers of numbers and remainders when you divide, modulo operators.
Sorry for the little spoiler alert there.
That's cool.
But spoiler tag. No, I'm just kidding. I don't care.
So we could, do a summation from I equals 0 to the string length of a string minus 1 of character I of our string. And then take that modulo 1000 or, whatever the size of the hash table is. And that's a perfectly legit hash function. That'll give us a position in our array to store any key. So ABC-123, I'll add up those 7 ASCII codes. If it's bigger than 1000, I'll reduce it modulo 1000. It gives me some number. Whatever that number is, that's where I store the data associated with it.
Is the idea for the module 100 to be if the square value, I think there's like, if the string length is more than 100, you're guaranteed you're going to have a remainder of 1 or something like that. Or I don't know how to say it, but
if we had a string that had, 1,000,000 characters in it, we know that if we add up the ASCII codes, we're going to get some huge honking number, right? It's going to be much bigger than 1000. And if I just try to use that as an index to my array, I'm probably going to segfault. Because my array only has values from index 0 to index 999. And so I need to make sure that I don't give it a ridiculous index. So by finding its remainder when you divide by 1000, you're guaranteed this is a number between 0 and 999. And so it's a safe location to access in my array.
Would you have to worry about palindromes in that case?
Yeah, so with this hash function, if we have the same characters in a different order, we're going to get the same result. Because, ABC, CBA, ACB, adding up the ASCII codes will give us the same value. So this is not a great function if you think you might have...
Could you, instead of adding them, append them?
Appending how?
Like, get the ASCII code and then just place it into a string, get the next ASCII code, and then put it after it?
And make a big long number?
Yeah, something like that.
That would be pretty cool. So you could definitely do that. It would not be good if you reduced it modulo 1000, but if you reduced it modulo something else, that could be a really interesting hash function, actually. So if I understand what you're saying, if you did something like, ABC, so we'll just do ASCII code for A, ASCII code for B, ASCII code for C, and we'll take that, 676,665, and, string them all together and then reduce that modulo something. That would be interesting. Now, if you do it modulo 1000, that's a not so great hash function because any number modulo 1000 is just the last 3 digits. But if you did modulo something else, particularly a prime number, this would be an interesting way to to get different hash locations.
Would that work for some sort of hash?
Yeah, I think so. I haven't seen that done, but I'll bet it's done in crypto systems somewhere. Because crypto people love like putting characters side by side and making big integers out of them. That's like how you start. Yeah. So if the black van pulls up outside in 20 minutes, we'll know it's a good idea.
My internet cuts out suddenly.
Yep. Sorry, class is canceled. All right. So this is not a great hash function, but you know, one way we can take care of making rearrangements map to different things would be, you know, maybe do I+1 times the ASCII code. And now ABC would be 65 plus 2 times 66 plus 3 times 67. CBA would be 67 plus 2 times 66 plus 3 times 65. And those are going to be different values. So the choice of a good hash function really depends a lot on the nature of your data. And if you understand the data from which your keys are going to come, you might be able to make a good choice, a better choice for hash functions. And there's a whole, you know, discipline to defining what a good hash function is and verifying the behavior of different hash functions and so on. But the main thing that we're concerned with is this question of collisions. Right, this idea that, you know, if we did ABC 1 2 3 and CBA 1 2 3 with a simple hash function like just add up the ASCII codes, they would point to the same place. And if I wanted to store, you know, CBA 1 2 3 and Phil, well, Phil would want to get stored at the same place that Nick is already stored. And this is an array. You can't have two things in one index. And so we'd either need to bump out the data that's already there, or say we can't store this data, or do something else. So that's what a collision is. It's when two keys point to the same location in the database.
Wouldn't that cause an error?
If we don't do something about it, it'll cause an error. It'll either cause data loss, or it'll cause us to say, you know, we can't store that data, even though there's lots of empty space in here. So we need a way to deal with it. And collisions are where your order of performance drops. If we don't have collisions, everything is order 1. We can have 1 million names in here. Well, if your table was at least 1 million, you could have as many names in here as you want, and to store a new piece of information, just hash it to an index, store your data there. To search for a piece of information, hash your key, go right there, there's where your associated data is. But collisions ruin this. Collisions will degrade our performance. And the more collisions, the worse the performance. So part of choosing a hash function is trying to pick a function that minimizes collisions. And so if I was using this to store license plates, and I was in a city where every license plate began with, you know, ABC, then you know, using those as part of my hash function doesn't do me any good. My hash function is basically, you know, just the sum of the ASCII codes of 3 digits. May not be a good function. So 2 main approaches we're going to talk about for dealing with collisions. So the first is chaining. And chaining is linked lists. And this is what you're going to do in PA3 if I make PA3 a hash table question. So here's our hash table.
I'm taking this way here. When you talk about collisions, is it when multiple keys point to the same data, or is it multiple data point to the same key?
It's multiple keys pointing to the same data.
Okay.
So if ABC 1 2 3 points here, and you know EE 5 6 7 points here, and this happens to also be Nick, that doesn't cause any problems. I could have every cell in here being the same data, because the key is what we're using to find our data. But if EE567 points right here, then I've got a collision, because I've got data associated with this and data associated with that, and they both want to get stored in the same spot. So yeah, it's a collision of what keys are hashing to. So what we can do is at each location in our hash table, we can store a sentinel node. And the sentinel node is the sentinel to a linked list. And so if I have, ABC123 associated with Nick, and maybe ABC123 maps to, index 174. Well, at 174, there's a sentinel node for an empty list. What I would do is have that point to a node containing Nick. And so this would have, one piece of data associated with it. And then if I have EE567 with Izad, and maybe EE567 hashes to index 1. So now I would have the sentinel node here point to a single node containing Izad. And then if there's a CAB123, and that's associated with Phil, and we're using our simple hash function that just adds up ASCII codes, well, CAB123 is also going to map to index 174. So we just add Phil to the end of the linked list so that sentinel's pointing to. So this points to Nick, this points to Phil. And we haven't lost any data, we haven't told them that they don't have space for Phil, and so on. And so this is called chaining, because you make these big long chains of entries. So what are the disadvantages of doing this? What are the problems?
I'm sure complexity.
Definitely complexity, because instead of just sticking our data in this array, we got linked lists, and we got to do all the stuff associated with linked lists, and we've got to put sentinel nodes in here, and all of that stuff. So definitely more complex. Sorry.
It could go from an order 1 to something else, right?
Yeah. So complex. It's not going to be order 1 anymore, because once we take our key and we hash it and we find, index 174, that's where our data would be stored. But now we got to search a linked list, and remember, searching a linked list is order n. If we have 100 names in here and we're looking for one particular name, we got to check every single name in order to know if the data we're looking for is in there. And when we store, this data in this linked list, we also need to store the key associated with it. Right? Our goal is tell me the name associated with CAB123. While we hash it to an index, we go to that index, we find a sentinel node. Now we start moving down here looking for a node containing that key. There's CAB123, and then there's the data associated with it. So our node structure would be, something like a key, a piece of data associated with it, and then a pointer to the next node. So it's a more complex linked list. And this is probably the biggest issue, the order of complexity. And if you're expecting a lot of collisions, if you think, you might have, a million things that hash to the same index, this may not be a great way to go. Because guaranteed, the more things that hash here, you're just going to have to, search through all the things that map to that. And we could try to make this, something more sophisticated than a linked list. We could make it a sorted array so that we can play high-low and divide it in half. We can make it a binary tree once we learn binary trees. We could make it another hash table and use a different hash function on the entries here and hope that, you know, all the things stored in here have fewer collisions when we use this other hash function. So there's a variety of things we could do, but it's going to make a performance negative impact. An advantage, though, is there's no limit theoretically to how much information we can store. Our hash table is going to be an array, and arrays, you know, always have a predetermined size. So on this example, my array can hold 1,000 entries. If I'm actually storing, you know, the data in my array, even if I'm very clever with my hash function, at most I can store 1,000 pieces of information in here, and then my array is just full. It's not just a question of collisions after that. There is nowhere left in here to store information. So unless I grow my array somehow, which you can do, I'm stuck. It's got a fixed amount of maximum storage. But if each of these entries is just a sentinel node, our linked list can grow as large as they need to until we run out of memory on the system. And so we get, you know, potentially unlimited storage in our hash. Although if these lists get very big, right, we're paying a performance penalty. And chaining is actually less complex than the alternative, which is probing. And so I'm going to have you use chaining for your next programming assignment. But let's talk about an alternative, which is probing. And probing, we're going to try to keep our order of complexity close to 1. But let's do a simple example. Well, I messed up my array. So let's do a simple example. Let's hash numbers, because I don't want to add up ASCII codes on the fly here. So we're just going to hash numbers. So our key is going to be a number, and the data is going to be, you know, some word associated with it. And our h of n is just going to be the sum of the digits of our number. And we're going to reduce that sum modulo 10 to get an index from 0 to 9. So if I want to store, you know, let's say I have a key 17 and Nick. 17 will hash to location 7, so I'll store Nick here. Sorry. Sum of the digits, 1 plus 7, so it'll be 8. And let's say I want to store 25 and you know, Bob. So 2 and 5 is 7, so this will hash to location 7, and I'll put Bob there. And let's say with the number 11, I want to store Sue. And so 1 plus 1 is 2, and so this is going to be where Sue gets stored. Everybody get what I'm doing here? We're hashing key data pairs. The key is an integer instead of a string, because I'm lazy. The data is a name. And our hash function says just add up the digits of this key, and then reduce it modulo 10.
What is the point of doing this instead of just a regular array?
because I might have something like, 999, and this is n, and 9 and 9 is 18, and 9 is 27, and I can reduce that modulo 10 and say, yeah, n should get stored at location 7, which is going to give me a collision at this point. But, this index could be arbitrarily large, and I don't necessarily want to have an array that can hold a million things, but I might have, some large number that I want to use as my key. So maybe these are phone numbers or student IDs. And if you wanted to store names associated with student IDs at Clark, well, our student IDs are 9-digit numbers. If we used an array, we'd need an array with, a billion elements in it. But we don't have a billion students at Clark. We have a few thousand. So we could get away with a much smaller amount of storage. So a hash would let us take that student ID and change it into, a number that would index this smaller array.
But this hash, it already looks like an array. Are those, say, the zeroth index of that hash, is that not initialized in memory at all? Or you initialize it when you...
You do have to initialize it, but no, you're right. This hash is just a simple array. What makes this a hash table instead of just an array, though, is that we don't... so hash bracket key, right? This is not just a simple index. This key does not have to be something between 0 and 9. This could be a string, a long number, something binary, right? What makes it a hash table is that we can take pretty much anything for this key and we can turn it into an index between 0 and 9 in this case. And it gives us a way to associate some piece of data with this key by storing it in this table at that given index.
I see. Okay.
Okay. All right. So this is a goofy example, I'll admit, because we don't usually hash with integers, but we might, phone number, student IDs, something like that. So our hash function just add up all the digits and reduce modulo 10, which means just take the last digit of the sum, right? It's not a great example because if we have more than 10 things to store, we're going to run out of space. But I want to talk about this as an example of how we can deal with collisions using this idea of probing. So here's the idea. Let's say we want to store n with the key 1999. So how do we do this? 1 plus 9 plus 9 plus 9 is 28. 28 modulo 10 is equal to 8. So this should get stored right here at location 8. But location 8 is in use, right? That's where Nick got stored. And we need some way to know that this is in use. You can't just look in an array and ask, is there something stored in this element? Arrays don't work that way. But we have, some flag saying, we've got something stored here. And we set that flag when we store something. So somehow, we know that there's already a piece of data stored at location 8. Where are we going to store n? So we basically look for another place to store this. So one way to do this would be just look for the next available spot. Since 8's in use, let's check location 9. Hey, 9's free. We'll store n right there. All right, and then let's store one more piece of information. Let's go with 287, and we'll put Izad there. All right, so 2 plus 8 plus 7 equals 17. 17 modulo 10 is equal to 7. So Izad should get stored at location 7 right here. Well, that spot's in use. So let's try the next location. That spot's in use. Let's try the next location. That spot's in use. Let's try the next location. Well, there is no location 10, so we go back to the beginning and we try location 0. And that spot's available. So we store izod there. Alright, that's the basic setup for using probing to deal with collisions. And we're not always just going to look for the next available spot. But basically, if you get a collision, we find some other location to store the data. And in this example, the other location is simply the next available location. That's not a great choice, but it's the essential idea. And this has, obviously a performance impact, because, it no longer took a single operation to store izod. We add up the digits, we reduce modulo 10, we find a 7. We should just store izod right there, but we can't. And depending on how much data is stored in here, we might have to go through a number of operations to find an open spot. And so this is starting to move towards an order n behavior. But it also gets a lot more complicated. So when we want to do a fetch, let's say we want to fetch the data associated with 287. Well, we take 2 plus 8 plus 7, we get 17. We reduce modulo 10, we get a 7. We come out to location 7. We look at this and we could say, hey, I guess the name we should retrieve is Bob. Well, Bob is not the name associated with 287. We don't want to return that. So we need to add some additional structure to our array to not only store the data, but store the key associated with it. So when we store Nick, we started off with Bob. When we store Bob, we'll store the key we used for that. When we store Nick, we'll store the key for that. Ann was 1999. Sue was 11. And izod was 287. Alright, so now we want to fetch 287. Well, we run our key through the hash function. We find a 7. We go to location 7. And we check the key of the data stored there. And guess what? That key is 25. Well, that's not what we're trying to retrieve. So we conclude that, hey, when we stored the data associated with 287, we might have tried to store it here, and this was already in use. We might have gotten a collision. Maybe we stored it in the next location. So now we check location 8. Well, the key of the data stored there is 17. That's not right. But since there's something there, maybe we got a collision when we tried to store it there. Let's check the next location. 1999, no, that's not right either. But since something's there, maybe we got another collision. Let's check the next location, roll back over, index 0. Hey, guess what? The data stored here is associated with the key 287. That's what we're looking for. We go ahead and we fetch the data izod and say, there's your value. So the fetch algorithm and the put algorithm are more complex because we need to deal with these collisions. And if we said, for example, fetch 377, 3 plus 7 plus 7 equals 17, reduce it modulo 10, we get a 7. So again, we'd come out here to location 7. This is key 25. That's not what we want. Go to the next spot, 17. Nope. Next spot, 1999. Nope. Next spot, 287. Nope. Next spot, nothing stored there. Then and only then we can conclude, hey, this data, there is no data associated with this key in our hash table. This is not found. But we're doing this linear operation. We're checking, check, 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 until we either find our data or we get to an empty spot. Alright, and it gets even worse with deletions. So let's say we delete Bob. So delete Bob. And so this goes away and this goes away. Again, we need to have some way of indicating that this has been deleted. We can't, make this spot of the array empty. There is no such thing as empty in a computer. There's always bits stored everywhere. So we need a flag that says, is there something stored in this location or not? So we delete Bob, we clear that flag, and basically say the spot's available. So now what happens if I try to find the key associated with, find the data associated with key 287? 287 running through my hash function, I get a 7, I go to location 7, this spot's empty. Do I conclude that 287 is not in my hash table? No. I need to record the fact that there used to be something here, which might have caused a collision when I stored something associated with 287. And so I'll hash this to location 7, I'll check here, I won't find key 287, but I'll find a flag saying there used to be something stored here. You might have gotten a collision, and I'll go through my probing and I'll try the next location and the next and the next, and then I'll find my 287. So our hash table needs to have a key, it needs to have a data, it needs a flag saying if this block is in use, and it needs a flag saying whether something's been deleted. And deleted is more than just not in use. Right, if we've never stored anything at location 1, and I'm looking for key 377, and I keep searching, and I get down here to location 1, and I've never stored anything in here, I can say 377 is not in my table. But if I'm searching, for 287, and I hash over here, and there's nothing in use right here, but I know there used to be something, I have to keep probing until I either find the thing I'm looking for, or I get to a spot that's not in use and not deleted, and then I can say it's not in my table. So our hash table gets more complex. It's an array of structures where our structure has, multiple pieces to it. And then the corresponding code gets more complex. So it can be, someone said this seems terribly inefficient. It can be, but remember, we're starting with order 1. Right? Running through a hash function, going to that location in your table, that's order 1. No matter how big your table is. And if your table is big enough, it may be that even if you encounter a collision, you may have to, reprobe once, maybe twice. And then you may find an open spot. And so maybe it takes you, 3 operations to store or retrieve. That's still order 1. Right? Order 1 just means fixed amount of time. That might be a large fixed amount of time. But if that amount of time doesn't grow very quickly as you increase the amount of data, it still turns out sometimes to be a really good algorithm.
The worst case would be OS, though, wouldn't it?
Worst case would be ON. If your table is very close to full, you might end up searching, every location to find your key, and then you're just basically, scraping through an array. All right. So what's left to talk about? I want to talk about some examples of probe functions, because this first one we've been using is very very simple. Just look for the next available spot. And then I want to look at some pseudocode and some of the details around using probing. for a hash table, and then we'll start looking at details of using chaining, which will be what you're going to actually code. Alright, let's do a 5-minute break and come back around 11. Let's see. Come back in a little over 5 minutes, and we'll dig into some more realistic probe functions. Alrighty, let's see. Chat comment, but it tends to be order n because eventually just about every spot will have the collision flag. So, ideally, your hash table should be bigger than, you know, the size you need to store every possible key data pair of interest. And theoretically, you know, if you keep storing more and more data into a hash, you're going to fill it up. And if you're chaining, you know, you're going to start building longer linked lists. If you're probing, you're just going to run out of space. But the idea is that you keep your hash table, you know, large enough that you're only using, say, you know, 20 or 30% of it. And so there's you know, a notion of a load factor, which is basically how full your hash table is. And your implementation of the hash table might say, you know, once your load factor exceeds 35%, we're going to double the size of the array. So now we can store twice as much stuff and your load factor goes down to like 17. And now it's going to take longer before you fill up 35% of that larger array, and at that point you're going to rehash everything into a bigger array. And so systems will generally dynamically adjust the size of the array as you store more and more stuff in it. Again, the main advantage is, you know, if you're storing student IDs, 9-digit numbers, to just use an array, which, you know, you'd use the student ID as the index, you'd have perfect hashing, you'd never have a collision, but you would need, you know, 1 billion elements in your array. If you only have 5,000 students, you could make your array, you know, 10,000 elements long, and if you can get perfect hashing with that, if you can minimize collisions, you've got a very efficient way to store and retrieve this information. So this business of probing, we can generalize this by thinking of a slightly more complex hash function. So our original hash function was, you know, something we just feed in a key and it gives you an index. But I'm going to make a more complex hash function that takes 2 arguments. There's a key, and there's also something called a probe number. And it returns an index. And the probe number is really, you know, just sort of the attempt number. And so the first time that I try to store a piece of information, I'm going to hash with the key that I'm using to store the data and a probe number of 0. And if I get a collision, then I'm going to use the same hash function with the same key, but a probe number of 1. And this should give me a different index. And at that different index, I'll try storing my information. And if that also gives me a collision, I'll try rehashing with a probe of 2. And so on and so forth. So this version of probing we were doing, where we said let's store the data in the next available spot, this looks like this. Add up the digits of the key, and then add the probe number, and then we reduce that modulo 10. So let's say I want to store 287. So I'm going to do 2 plus 8 plus 7 plus the probe number, which is 0. Reduce that modulo 10, that's going to be a 7. And this was when we were storing Izad, and location 7 had Bob in there before we deleted it. So that was a collision. So then we would say let's rehash 287, 1. And our hash function says, this is going to be the sum of the digits of the key plus the probe number, reduced modulo 10. Well, 2 and 8 is 10, 17 plus 1 is 18. This is going to give us an 8. And so our second hash attempt would take us to location 8, which was another collision. And so we'd hash again. Which would give us a 9. And that also gave us a collision. And so we would end up making a fourth attempt. So we pass in an attempt number or probe number of 3. And this would be 2 plus 8 plus 7 plus 3 modulo 10. 2 and 8 is 10. 10, 20. 20 modulo 10. This is a 0. And then at that location 0, we found an open spot. And so we were able to store Izod there. So this is called linear probing. And it's effectively just looking for the next available spot. And sometimes that's a good function, but if you have a lot of things that are going to hash to the same location on your first attempt, then every one of those things is going to try to go to, say, spot 7, and when you rehash, it's going to try to find the next available spot. Well, if you have a lot of things that are going to collide with this location, linear probing is going to tend to group all of those things really close to each other in your array. And so that's something called clustering. And clustering basically looks like this. Here's our array. And we've got a bunch of data stored here, and a bunch of data stored here, and a bunch of data stored here. And then you got all this open space that you're not using. That's not a very efficient use of your hash table. What you'd really like to do is have your data distributed more or less evenly throughout your hash. So if we were storing names, let's say hash of name equals ASCII code of first letter. And let's say, our hash table goes from 0 to 127. Would this be a good hash function for storing names? What do you think?
It says just the first letter.
Mm-hmm. First letter of the first name.
Well, I mean, won't there only be 26?
Yeah, so first of all, there's only 26 letters, so we're never going to have anything with an ASCII code, below 64 or bigger than 97. So all of our names are going to hash to something inside here. Actually, that's not 97, it's something even smaller. Right, and none of our names are going to hash to anything up here or anything down here. So by itself, that's not a very good function. Also, we don't have a lot of names that begin with the letter Z. We have a lot of names that begin with the letter J. And so you're going to tend to get a lot of collisions. And you're going to tend to be clustering, around certain letters. And so this would be a horrible hash function for storing, names, for example, in English. But if I were to, add up all the letters in the name and then reduce that modulo 127, that might be a better hash function. And there aren't a lot of names where if you just reverse the order of some of the letters, you get another person's name. Right? So simply adding up the ASCII codes and reducing mod 127 might be a good hash function for names. Not such a great function for license plates. So clustering is the tendency of your data to occupy sections of your hash table while leaving other sections mostly empty. In other words, it's your deviation from the ideal, which is evenly distributed data throughout your hash table. And it's a function of the data itself and also the hash functions that you're using. And so linear probing, where we just take your regular hash function and we just add the probe number to it, will tend to create a lot of clustering if you have a lot of initial collisions. And so there's other ways we can probe. So quadratic probing might be something like this. So maybe, we add up the ASCII codes of each thing in the key or each digit or something like that. And then maybe we add the square of the probe number. And we reduce that modulo the size of the hash table. And so in this case, if we wanted to hash 287, something associated with 287, on our first attempt where our probe value is equal to 0, right, this is again, 2 plus 8 plus 7 plus 0, 17 mod 10, that gives us a 7. If that gives us a collision, we'll rehash, and we'll add 1, that'll give us an 8. So same as before. But on our third probe attempt, where our probe value is equal to 2, we would do 2 plus 8 plus 7 plus 2 squared. And so 10, 17 plus 4 is 21. This would give us a 1. And if we jump down to location 1, we would find, hey, that spot's available. And we would have stored Izod here instead of checking location 9 and then going up to location 9 to 0. So quadratic probing will tend to spread out your data following collisions. And if you get, 5 collisions in a row as you try to store a piece of data, right, on the 6th attempt, you're going to, jump 25 spots down in your hash table. So it's going to tend to break up these clusters and distribute them throughout the table.
I think this method is pretty useful until you get a lot of data already in the hash, in the hash already.
Right.
Because then now it's all based off of luck or time, whether you are able to hit that empty spot.
Yeah, exactly.
So eventually you have to go back to using the first probe algorithm.
So this is where the load factor comes in, the fullness of the table. And it's basically something from 0 to 1. 0 is empty, 1 the table's completely full. If the table's completely full, you're going to get a collision. Doesn't matter how clever your hash function is, it's going to take you to somewhere in the table, and if everything is full, it's going to be a collision. If your fullness was 0.5, all things being equal, you got a 50% chance of getting a collision. So this is where implementations will do things like keep an eye on the load factor and say, you know, if the load factor is above a certain amount, let's make the table bigger. And usually in the background, something will create a larger array, rehash all the information from the original array to store it into the bigger array. You're going to use a different hash function, right, because you have more indices to choose from. It'll rehash everything, and then it'll start using that bigger table. And here's the thing that I keep coming back to, right? As an abstract data type, we don't care about hash functions. We don't care about probing. We don't care about chaining. We don't care about load factors, quadratic chaining, linear chaining, quadratic probing, linear probing, all of that, right? None of that is relevant to the user, other than, you know, this hash function is kind of weak. It's really slow. But as far as how somebody's going to use this hash function or this package, right? They just, you know, initialize, fetch, put, delete, traverse. But the implementation of it is doing all of this stuff. It's saying, oh, you know, here's the key they're looking for. Let's run it through a hash function. That's a collision. Let's rehash with a different probe number. And, you know, there's something that was deleted there, so let's rehash again, and so on and so forth. Right? So this is all the other side of the firewall. This is all the implementation details. And they should be transparent to the user, other than, like I say, maybe performance. Maybe the user notices that, you know, this set of functions is really fast and this set of functions is really slow. So they may notice that, but they're not going to know anything about, you know, how many collisions they got, or how full the table is, or how big the array is, or whether it's chaining or using probing, or anything like that. We want all that information hidden from the user, and the user just sees, you know, this sort of clean interface that's independent of the implementation.
Besides, it's all in C, so they barely even notice anyways.
Yeah, yeah. Although if you were storing, like, you know, 1 trillion pieces of data, it starts to be more noticeable sometimes.
0.1 seconds instead of 0.00.
Yeah, yeah. Well, I mean, you do like a Google search and it tells you how many hits it found, you know, and it's usually at least in the billions, and that's pretty remarkable to search through a set of data that size.
Well, yeah, I use some crazy indexing and whatnot,
Yeah, yeah.
which are all written in Python, funny enough.
Are they really?
Yeah, Google's crawlers are all written in Python.
Oh, okay, yeah.
They don't actually need to loop through things, they just index websites.
Right. Yeah, they got some good secret sauce. So we can have lots of different hash functions with lots of different probing techniques. We might, you know, use an entirely different hashing system. We might, you know, add up the ASCII code of characters on our first probe attempt, and on the second probe attempt we might, you know, multiply the ASCII codes of each character, and on our third probe attempt we might, you know, do a weighted positional sum of the square of ASCII characters. And so again, you know, this depends on the nature of the data and a lot of understanding of how hash functions will work and how probing will work. And a lot of it depends on the size of your hash table also. Not just how big it is, but actually, you know, what the actual size is. And it's not always that bigger is going to perform better. And so depending what you're doing to turn a key into an index, suppose we use a hash function like this. This is a linear hash function. So key and a probe. So maybe we'll add up the ASCII codes of our key, and then we'll add 5 times the probe number, and we'll reduce that modulo, you know, the size of the hash table. So what is this doing effectively, right? Suppose we hash a key and it brings us to this spot right here with a probe value of 0. Well, if we set our probe value to 1 and we rehash, it's going to try a spot not right next to this one, but 5 spots down, right? We're going to add 5 times 1. So it's going to try a spot right here. And if we get a collision there and we hash with a probe equal to 2, it's going to try a spot 5 spots below this one. And if that's a collision, we'll go another 5 spots down. So we're going to jump by 5s instead of just checking the next location to try to break up that clustering, right? To try to keep things from all gathering up around this one spot. So this is an example of linear probing, but instead of just checking the next location, we're going to, you know, go up by, say, 5. Well, if our hash table had a length of 100, right? If our array was an array of 100 elements, this is a really bad choice for a hash function. Any idea why, thinking about the probing, this would not be a good choice for a hash function? This gets into some CSE215 stuff. Let me make n 10. Suppose our hash table has a length of 10. And our hash function is, you know, add up the characters of our key and then add 5 times the probe number and reduce that.
Remove 5 of the possible ones?
Say again?
You just remove 5 possible indexes, or, you know, places you can store that information. 0 through 5 are now always going to be empty.
You might get back there if your keys added up to 1, right? On your first probe attempt, p equals 0. This would hash to a 1. So you might still be able to use those, but I think you're thinking in the right direction.
You'll go out of bounds really easily.
If you go out of bounds, we're going to roll back over by doing this %10.
I don't know, it just seems like it's going to skip a lot of stuff a lot of the time.
Yeah, flesh that out. You're right, that is what's going to happen. Can we explain why?
I don't even really understand how this works. Anyways.
So suppose I want to hash. Let's just do the string containing the letter A, which is ASCII code 65. So my hash function would say, okay, take the ASCII code of this, which is 65, 5 times 0, that's going to be 65, modulo 10. So A is going to get stored at location 5. Okay, now let's store, let's see what would happen if we hashed this with a probe attempt 1. Suppose something was at location 5 and we got a collision, and we rehash with a probe value of 1. This is going to be 65 plus 5 times our probe value of 1. So 65 plus 5 is 70, modulo 10. Our next probe attempt, right, attempt 1, is going to try to store at location 0. So our first attempt tried to store right here at location 5. Our second attempt is going to try to store at location 0. And suppose that causes a collision also. What happens on our third attempt? What's the hash function going to return?
It's gonna be like the well, I was trying to think of like what's module 10 of 75.
Mm-hmm. This is going to be the ASCII code of A is 65 plus 5 times our probe number is 2, which is going to give us 75, and when we reduce that modulo 10, we're going to get 5 again. And so our third attempt is going to try this spot.
So you're going to get a lot of 0, 5s, and 10.
Yeah, and 10 is actually 0, because 10 mod 10 is going to give us a 0. So we're just going to get 0s and 5s. And multiple probe attempts are just going to give me either this location or that location. And it may be that, you know, I've got open spots all over here, but, you know, no matter how many times I probe, it's going to say, nope, that's full, nope, that's full, that's full, that's full, right? And so this is not a good probe function because it's not making good use of the entire hash table. But it turns out that if I had made my hash table only 9 elements long, this doesn't happen. My first attempt would be 5. My sixth attempt, well, I got to do different numbers. But if you do the different numbers, right, this and this and this will all give me different numbers. And in fact, I can probe 9 times, and I'm guaranteed I'll get 9 different indices. Which means on my first 9 probe attempts, right, calling my hash function with an argument from 0 to 8, I will get a different index every time. And that's just by changing the length of my table from 10 down to 9. And so here's the magic recipe. We want to know that the greatest common divisor of 5, the scaling factor for our linear probe, and n, the length of the hash table, we want the greatest common factor to be 1. In other words, we want these numbers to be relatively prime. And in 215, when we talk about Euclid's algorithm and prime numbers, we can actually find a reason why this is a really good way to make a hash function. And it ties into trying to do division in modular systems. We're not going to worry about that here. It's just an example that, something as subtle as, making the hash table 1 element shorter can drastically improve your performance. And one easy way to make this happen is to pick a hash table whose length is a prime number. So 11, 13, 101, something like that. So there's all sorts of stuff that goes into this.
It's like years.
Yeah.
Gotta have a prime or co-prime number.
Yep.
When I figured that out, that I never knew about that, and I figured that out about a month ago. It's super interesting.
Oh, cool. Nice. All right, we ready for some pseudocode?
But is it 5 is prime, which is interesting.
5 is a prime, but 10 is a multiple of it. And that's exactly why this was happening. If our hash table was a length of 15 or 20 or 100 that I originally said, right? Starting with an initial hash with probe 0, after a certain number of times you're going to come back to here, but it's not going to be when you've tried every other location in your table. If our table length had 100, after 20 probe attempts we will come back to where we started. And after 20 attempts we can't have checked all 100 locations. Hey. But if our table length was 101, we're guaranteed that it would take 101 probes before we'd have tried every location and come back to the original. And those are details that, like, other people can figure out. We're not going to get that fancy because we're just trying to understand the concepts of how a probe function works and how it is used for collision management and so on. But if you were actually trying to implement an efficient hash function, you would find a mathematician or do some research and look at some papers and figure out, you know, based on the parameters of the data that you're going to be hashing and so on, what makes a good hash function? What are the characteristics and so on? But we won't worry about that. And like I say, when you program this, you're going to use chaining instead of probing. So we're not going to have to worry about this. But I want to go through this in detail because I want to make sure people understand how probing works. So let's look at some pseudocode. So let's suppose our hash table is an array, and we said we're going to have 4 fields in each element. So we're going to have a key and a data, and the data is associated with the key, and then something which says, is this element of the array in use? And then something which says, have we deleted this element from the hash? And we're going to initialize the in-use entries to all be 0 and the deleted entries to all be 0. So our initialize function might be, you know, maybe malloc a bunch of space for a big array, and set in use and deleted equal to 0. And that's all you need. Doesn't really matter what's stored in the key data pair. If we say it's not in use, we're not going to look at it. And if we say it's not deleted, if we come down here and we see it's not in use, we're going to say, okay, if that's, you know, if we're looking for something, it's not found. If we want to store something, we'll store it right there. So initialization is just, you know, creating the array, which we might do with a malloc instead of, you know, statically, and then setting these flags to 0. And I'm going to suppose that we have a hash function h, which takes a key, whatever that is. I'm going to probably assume it's a string, but, you know, takes whatever type of thing our keys are and returns an integer. And let's suppose that our hash has a length of hlen. So what's the index of the last element in our array?
Element length minus 1.
Yeah, so hlen minus 1. Good. And so we've got some hash function that we've already written or we've been given or something that takes a key, gives us an index between 0 and hash length minus 1. And I'm not going to worry about what this function is. I just want to see how to use it to do put and fetch and traverse and delete. So pseudocode put key comma data. Actually, let me make this hash function, since we're probing. It takes a key and it takes a probe number, and a temp number. Alright, so how do we put a piece of data associated with a key into our hash function? So location, so let's do p equals 0. That's our probe number. And then our location equals hash of key, comma, probe. And then if that location in our hash table is not in use, then we do the following. Then we say hash bracket location data equals whatever data we want to store. We'll set the in-use flag to 1. And that should be all we need. So maybe we'll return 1 to say success. But if when we hash this we got to a location that's in use, then we want to increment our probe attempt and go back and rehash. So now P will be equal to 1. We'll hash our key with a probe value of 1, get a new location, see if that location's in use. And if it's not, we'll go ahead and we'll store our data at that location. We'll say it's in use and we'll return. And then we need to have some way of knowing if this is futile, right? So have we tried every possible location? So maybe we could say something like if P is bigger than the length of our hash table, we'll return 0. Say again?
Wouldn't it just be if P is bigger than -1? Or
Probably, but I didn't want to think too hard. So I'll just waste an extra hash attempt. But let's see if we really want to think about it. So if P is equal to, if our table is 5 entries long, we should hash with probes values of 0 through 4. So 4 should be a valid hash attempt. So we should kick out when it's greater than or equal to that. So yeah, if it's greater than, yep, you're right. So if it's greater than hash length -1, then we know we've tried every location. The other thing you could do is you could check to see if the location you got is the same as the location you got when you hashed with a 0. And if you have a probe function that's, not using the entire table, that would tell you immediately that, hey, I'm trying with attempt 7, and I got the same value I got with attempt 0. Now you know you're looping. And so you could say, okay, our table's full. So somehow, so you don't infinite loop. But that's pretty much your whole put function. It's pretty straightforward, right? If we didn't have collisions, we would simply, hash our key to a location, and we'd store our data at that location, set the in-use flag. We just have to do this extra bit to see before we store, is that location already in use? And if it is, bump up P and hash again. So that's the put function, and it's pretty straightforward, particularly compared to fetch. Alright, so how do we fetch a key? Set your probe number to 0, hash your key with that probe number. That tells you where your data might be stored. If the data at that location is in use, and the key matches what you're looking for, then we found our entry in the hash table, and we can just return hash bracket location dot data. And here we found it. So take your key, hash it. If that block is in use and the key matches what you're looking for, you found your data. Return the data and you're done. And we got to check that in use flag, right? Because if we had something in here that was deleted, this part would still find it, right? If we happen to have gibberish in our table, it's possible that the thing stored at some, key location in here might match the key we're looking for. But if we don't have that in-use flag set to 1, we know that this isn't actually something that's stored in our hash table. So find your location. If that block's in use and the key matches, you're good. You're done. If the in-use flag is 0, and the deleted flag is 1, so this block is not currently in use, but the deleted flag is set, saying, hey, there was something here before. Then we have, possibly we are seeing the after effects of a prior collision when we tried to store the data. Or if this block is actually marked in use, right, and the key didn't match, because if it matched we would have returned previously. So if either this block is not in use but there was something there, or this block is in use but it's not the key we're looking for, then we need to reprobe. So we need to increment P, and we need to go back up here and try again. Otherwise, we didn't find the data you were looking for. We didn't find the key you were looking for. Alright, so to fetch a key, hash it to an index. If that index is marked in use and the key that's stored there is the key we're looking for, we found our data. You can go ahead and return it from the hash. If that spot's not in use but there was something in there before, or if that spot is in use but it's not the key we're looking for, we've got a collision we need to reprobe. So bump up our probe factor, go back and rehash with that new probe value, and repeat all of this. And this will keep going until the code is not, the entry is not in use and it's not deleted. Right, so if you get to a spot in the table where you have an entry that's not in use but there also was not something there previously, and we haven't found our key yet, at that point you can say your key is not in your hash table, and so we can return a not found. Alright, so that's the fetch algorithm. And then delete is a combination of search and then updating your deleted flag. So let's delete a key. So start with your probe of 0, hash your key with that probe value to find a location. If at that location we find the in-use flag is set to 1, meaning there is a key data pair stored there, and at that location the key matches the key that we're trying to delete, well, we're going to delete that entry. How do we delete the entry? Set the in-use equal to 0 so that, when we're going through trying to store something, we'll know that that spot's available. But also set the deleted flag. Set it to a 1 so that if we're searching and we come to that spot, we don't stop searching and say, oh, I guess your data is not found. We know that we have to continue probing. Otherwise, bump up your probe value, go back and try again. And on these loops, right, we need to do something to make sure we don't loop forever. So, you know, bump up your probe value and see if it's equal to the hash length, and or, you know, something. So go back, and basically this is searching for the key in our hash table. So look for the next location, see if it's in use and the key matches. If it doesn't, probe again and do that check again. If you eventually find it, set the in use to 0 to say the spot's free. Set the deleted to 1 to say if you come to this point searching for something, keep searching. Alright, what if you wanted to print the contents of your hash table? How could you do that? Just kind of in like plain English. Forget about code for a minute. How would I print the contents of my hash table? Let's say I want to print the key value pair, key data pair for everything stored in there.
You wouldn't have to care about deleted or if you would you just, I don't know, loop over it, I guess?
Yeah, exactly. Just loop over it. So we don't care about the deleted flag. We do care about the in-use flag. So a basic print function just to print out key data pairs could be something like iterate over every element in our array. And if that element is in use, then just print out the key data pair. And there you go. So that's pretty simple, right? Iterate over each element, and if that element's in use, print out the key data pair, and you're good to go. Yep, you got it. So if we wanted to put that in the form of an iterator, remember for an iterator we had a pair of functions, a start iterator and a next key iterator. And so this is getting stateful, right, like PA2's main program. So our start iterator function might do something like next index equals 0. And we could have an evil global called next index. And it would be a variable outside of our function, so its value persists. So that after we set next index to 0 and we return, that value is still valid, right? So if we declare next index inside this function, once we exit this function, that value is gone, and no other function can access it. But if I declare this next index outside of this function, any function from this point on down can access next index and see this integer. So my start iterator is just going to initialize this to 0. And then my next key function will do the following. Actually, maybe I'll start this at -1. So my next key function will do the following. I'll increment next index, and I'll say if hash bracket next index dot in use equals 1, I'll return hash bracket next index dot key. So every time that I call my iterator to get a new key from my hash table, I'll bump up this global variable called next index. So the first time I do this, it'll change to a 0. And I'll check to see if that location in our array is in use. And if it is, I'll return the key stored at that location. If that location is not in use, I'll just come back up here and I'll try the next location. And if that next location is in use, I'll return that key. If not, I'll bump up my index and try that next location. And I'll just iterate over that. So, you know, if this is my hash table, I'll start off and next index will be -1. So the first time I call next key, next index will change to 0. I'll give you back, you know, 287. The next time I call next key, it'll bump up next index to 1. That's not in use. It'll bump it up to 2. It is in use. It'll return an 11. The next time I say next key, it'll bump up next index to 3, and then 4, and then 5, and then 6, and then 7. And when it gets to 7, it'll say, oh, that's in use, and it'll return that key, 25. So I called start iterator, and the next 3 times I called next key, I got back 287, 11, and 25. And to make sure I don't, you know, seg fault, I need to make sure this index is valid. So I'm going to bump up next index, and I'm going to say if next index is bigger than my hash table length -1, because this is the largest legal index. So if I exceed that, then we're done iterating. So I'll return null or something, you know, an empty string, an empty key, something to tell the caller, hey, our iteration is done.
What would probably be even simpler would just be if it equals the hash length, right?
If it equals what?
If instead of bigger than the hash length -1, just equal the hash length.
Yeah, you can see if it's equal to hash length.
Yeah, sorry.
Yep, yeah, that's the same thing. And I think, you know, some part of me internally, when I first learned programming, I didn't quite trust computers. And so I was afraid, you know, maybe it would, like, jump up by 2 at some point and it would get past hash length, but it wouldn't actually be equal. And so I usually code with that. It's like a superstition thing. And I know some other people who do that. So there's, like, you know, psychological analysis you can do on people by looking at their code. So this is the insecure coders version.
100%, I understand.
Yeah. Same thing with, you know, if you have a switch statement and you know that you've covered all the possible cases, sometimes you just have to put in a default case anyway, because it'll keep you awake at night. And I've actually... Yeah, I've had times where that's actually, like, kicked in after, like, operating system upgrades and stuff, where a new case popped up that I hadn't covered, and I was working a job once, government think tank, and I left the job, and about 2 years later, a friend I had been working with called me up and said, hey, your code just printed out an error message that said, eat hot death pig. And it was one of these, you know, extra cases I had put in for the default case that never should have happened, but they had upgraded the operating system, and now this unexpected, you know, 4th case occurred, and so they got this bizarre error message, and that kind of freaked them out. So
you
that...
say, you'll do consulting for $300 an hour?
Yeah, exactly. So that and rip in space-time continuum are my 2 usual should not happen error messages.
What was the first one?
I think it said "Eat hot death pig." I don't remember why. It's something my friend and I used to say to each other a lot. All right, so iterators are pretty straightforward for a hash table, right? It's literally just go through every element, and if it's got something stored, you know, that's the next key data pair that you're interested in. But, you know, if you did not have some sort of iterator or a print function or something like that, a main program would have no way of saying, show me everything that's in the hash. Because the main program is not allowed to interact with this array. It's not allowed to look at the in-use flags or the deleted flags or things like that, right? That violates this abstract data type firewall. So we usually provide some kind of iterator to let the system have a way of working with this data. All right, so questions about that. And again, you know, I don't expect you to memorize this. I don't expect you to, you know, be able to write this from the top of your head. But my goal is that, you know, with some understanding of how hash tables work and this idea of you know, how we delete things and so on, if you wanted to sketch out pseudocode for a put function, you should be able to eventually come up with something, you know, along these lines, right? Might not look exactly like this or even approximately like this, but, you know, something that would basically do the steps for adding something using probing. So hash with a probe attempt of 0, see if it's available. If it is, store it there. If not, increment your probe value, rehash, and keep going. So yeah, PA3 is going to involve hash tables. Nothing to do with PA2. So yeah, you did not miss the memo. But for PA3, instead of probing, we're going to use chaining, which is going to involve linked lists. So PA1 will tie into PA3. All right, so to actually code this is you know, just a bunch of legwork, right? So we could make an array of structures. So what might our hash table look like? Let's make a structure called a hash entry. And it's going to have a key, so let's suppose our key is a string. And let's suppose our data is a string. And our in use and deleted are just going to be integers.
Wait, so with the associative array, can you actually have a string point to a string?
Sure, we could store anything we want for the key and the data.
Okay.
Yeah.
That was pretty cool. Like if you have somebody's like first name and last name, you can kind of group them together, or, well, you say you can't have multiple keys point to the same data, but.
I said you can't have what?
Multiple keys point to the same data, to the positive collision.
Right.
So because I was thinking like, how would you get multiple names associated with the same last name?
So what are we thinking of in terms of what's the key and what's the data here? Just as an example.
I think it means having like the first name in an array and the last name in an array.
So like if
Yeah, like,
go ahead.
Yeah, like the last name being the data.
And the first name being the key?
Yeah, but the problem is that the first name, you can only have one key per point to a data. So if you have like if you have MA5, then you have like 5 things pointing to the same data.
Right.
Point out. Sorry if those confused me earlier.
Right. So John Smith and John Jones, you could not store both of those in the table we're describing. If the first name is the key, right, we could only have one piece of data associated with that.
Yeah.
But, you know, if we use the first name, last name as a key, so, you know, John space Smith, John space Jones, and then the data we were storing was, you know, their address or something like that, right? That would work fine unless you had two people with the same first name, last name. And so this is where, you know, you get to your Clark email addresses, and it's, you know, j.jones213, right? So there's a number added to the end of the first initial period last name to make it unique, so that you don't have two entries with the same key. So you can start playing those kinds of games. So yeah, our individual hash entry could be, you know, some kind of structure, which I'll call a hash entry. And, you know, in this case, it's got strings for key and data, but they could be, you know, pointers to anything, basically. And then an in-use flag and deleted flag. These just need to be bits. Straight C doesn't work with bit fields. It kind of fakes it with short integers. So, but we can just make those integers. And by the way, you know, there's fancier ways you can do this. You can get away with a single flag with multiple values. Because, you know, we only need to know if it's not in use, not deleted, not in use, but deleted, in use. So we could use a composite flag that captures all that information, but we don't need to worry about that. I keep looking over there because that's where my camera usually is. It's actually over here now. So that's why I'm staring away. So there's what a hash entry looks like, right? And then our hash table could be something like this. Struct hash entry hash bracket 1000. And that would be, you know, an array of 1,000 of these things. And so this is something that's defined at compile time. And before our program actually starts executing, this space for the hash table has been allocated, right? And before we get to our first executable statement of C code, right, something has set aside space in memory for 1,000 of these things. So there's 2 pointers for 16 bytes and 2 integers for another 8. So 24 bytes times 1,000, 24,000 bytes minimum have been set aside somewhere, and hash is the address of that first byte. So that's static, and if we want to make this thing larger, there's really no easy way to do that. No clean way to do that. So if we wanted to grow this dynamically, we could do something like this. Struct hash entry star hash. So hash is going to be a pointer to one of these things. Remember, anytime you have an array of blah, that variable is actually a pointer to blah. So by making this a pointer to a hash entry, this is an array of hash entries. But it doesn't point anywhere yet. So somewhere before we try to use this as an array, we have to allocate space. And so we could allocate, you know, 1,000 times size of struct hash entry. And this is dynamic. This happens while our program is running. And the advantage of doing this dynamically is that this 1,000 could be a variable. This could just be some, you know, how big do you want to make the hash table to begin with? And maybe in your init function, when you call init to say, you know, I want to create a hash table, maybe you accept an argument which says, how much stuff do I want to store in there? And if I say I want to store 100 things, maybe I would use that variable times 10 and use that to tell me how big to make my hash table. So this is, you know, the runtime version of doing this. And then finally, if you had a hash table and you wanted to make it bigger, well, if you're going to use a bigger hash table, right, you're going to go from this to maybe twice your hash table length minus 1. One way to do that is to iterate over all the key data pairs stored in here. So you iterate over this, you pull out each of your key data pairs that exist in this table, so check the in-use flag, right? And for each of those, you use some new hash function, right? Because at different table length, you're going to have a different hash function. At least, a different modulo when you reduce your arithmetic. But you take each key data pair and you basically store it into this new hash table. So you rehash it and you find an index in here and you look for collisions and so on and so forth. And effectively, you just pull out each thing from here and you add it to this bigger table. And then when you're done, you say, okay, here's my hash table. And if you're really good, you can do this in the background. Inside your add function, your put function, every time that you store something, you can check to see what the load factor is. And you can say, hey, if the load factor is bigger than, 35%, let's grow the table. And so you go back to the user, but you start another process running in the background that creates a new array that's twice as big as the old and starts going through here. And every time it finds, a piece of data stored there, it stores it in this bigger table. And then when it's done, it seamlessly switches over so that when you try to interact with your hash, you're working with this bigger table now. And so like in Java, when you initialize a hash table, you can specify what kind of load factor. I think you can specify what kind of load factor you want to maintain. And it'll automatically increase the size of the hash table if you start adding more and more stuff. And this is transparent to the user. The user just calls put. And they don't know that when they put this one piece of data in, all this other stuff happened. Alright, so that's a lot of stuff. Like I said, I'm looking for overarching themes here, right? Basically how we use this idea of probing to deal with collisions. So hash to find a spot to store something, and if you collide, rehash, right? And we use a different value for the second argument, the probe value. It'll give us a different location to try. And we keep hashing like that. Alright, so Wednesday, we'll talk about chaining. And chaining is what we're going to actually use for PA2, so for PA3. So, wow, is PA2 this coming Friday? Yeah. So I'll post PA3 in a few days. And then we'll talk about chaining and we'll go through that. Alright, cool. Have a good one then, and I'll see you in 2:15 if you're in there. If not, I'll see you on Wednesday or office hours tomorrow morning. Alright, thanks.